Okay, so here's what we were talking about last time. We were talking about how to do change of basis, but specifically for a linear transformation. Now, so just a quick reminder, what we're doing with all this basis business is we've got these abstract things we need to be able to deal with. Vectors in an abstract vector space, right, can be kind of inconvenient, awkward, certainly inconsistent in how they look. Linear transformations between vector spaces. Again, there's lots of different weird ones that we've already seen. So they always look a little different. They can be a little bit unwieldy. So the idea is that we use bases as a way of giving these otherwise abstract things, vectors, linear transformations, a consistent and convenient appearance, I'm going to call it, and we can represent them in consistent and convenient ways. So we represent vectors with, intuples, right, ordered lists of numbers in Rn. And we represent linear transformations with matrices. Okay, so what this diagram represents is a situation we talked about last time. Let's suppose that we have some linear transformation from V to W. And we already know, let's say, as represented by the diagram, that's sort of the back face, if you will, of this sort of prism-shaped diagram. We already know how to represent T with respect to a pair of bases, script V and script W, let's say. So we already know what this matrix is. On the other hand, what we would like to be able to do is to represent T with respect to this other pair of bases, V prime in the domain instead of V, W prime in the target instead of W. All right, so how would I go about finding that matrix? And the answer that we discussed last time, a little bit quickly, because it was the very last thing we did, is to observe that that's a change of basis diagram, and that's a change of basis diagram. And we already know how to do change of basis for vectors. So we already know how to do that and that. So we can relate, let's see here, we can relate on the bottom of this diagram, and let me get rid of the rest of this stuff now. We can relate the matrix representing T with respect to our new bases to, instead, the matrix representing T with respect to our old bases by way of the fairly clear observation that going across like that is the same as going over and across and back like that. Okay, and that is what gives us this equation right here. Okay, so again, I like to think of it in terms of the diagram. On the other hand, and we'd sort of talk through this easier alternative point of view where you can just sort of motivate this directly, that if someone comes to you with a vector in V prime language and says, hey, I want you to execute the linear transformation T, and whatever comes out, I want you to express the answer in W prime language. Then you just observe that these three steps do that, right? If someone has come to you in V prime language, if you translate to V language, execute the linear transformation with the understanding that the input is in V language, except that your result's going to come out in W language, which is not what we wanted. We want our result in W prime language. So find, translate from W to W prime language at the end. Okay. So different, arguably easier point of view. Now, I hope you won't throw out the diagram completely. There is some really nice stuff that this diagram could do for you. So, for example, there's at least one homework question. I don't remember the exact details, but where the question asks you to go through some calculations. Like they give you a vector, and then they ask you to apply the linear transformation and write the result in W prime language or something like this. And then maybe later they ask you to take that same vector and do that, and then this, and then that, or something along those lines. Notice that even though those two calculations don't immediately appear to have anything to do with each other, having this diagram written out, you can see that the results of those two calculations are in fact very closely connected. You see right here from the diagram, right, the output from the green calculation, the output from the purple calculation, that's just a change of basis on the same output vector in W. Right? So if you keep track, if you have a diagram like this representing all the calculations that you've done, all of the sort of nodes in the process that you're dealing with, you can keep track of where you are and thus find perhaps an easier path to getting where you want to be. So very useful sometimes for your consideration. All right, let me show you an example where this is a very useful concept. So suppose I want to find some matrix that has the following two arithmetic features. This is kind of a tricky question if you think about it. I mean, how would we go about finding a matrix that sends this vector to that vector and sends that vector to this other? How would we do such a thing? Okay, well, here's the way I'm going to approach this. By the way, there is a sort of a brute force. Let's ignore the brute force way to solve this problem, which is to write out the coordinates of A as A, B, C, D, and to realize these two vector equations as being, in fact, four scalar equations. We have four equations and four unknowns, and you could just brute force it like that, but it's a lot less slick than what I'm about to show you, a lot less convenient. Okay, all right, so here we go. Step one, these equations, arithmetic equations, let's view these as statements with respect to the standard basis. So, in standard basis language, this A represents some linear transformation. 1, 3 are the coordinates with respect to the standard basis of some vector. Right? How would we describe that vector? Well, we'd usually just call it 1, 3, right? And insist that that is the description with the understanding it's with respect to the standard basis. Okay, etc. Okay, so A represents some transformation. 1, 3, that's the coordinates with respect to the standard basis of a vector. Let me just give it a name, just to avoid calling it 1, 3. Let me call it V1, etc. All of this is standard basis language, and we recognize that by, and now we can give names, coordinate-free names to the matrix and vectors participating in these equations like this. Okay. All right, so now then coordinate-free, these equations, which are intrinsically written with respect to the standard basis, let's just sort of lose the language. Let's just say all this, coordinate-free with respect to not with respect to anything. Let's just make statements about the vectors and the transformations in the abstract. So we get that. Okay, so punchline, we recognize that is just a particular basis representation of what is in fact a linear transformation and some vectors. Okay. All right. So, I claim that this is a convenient basis for understanding the linear transformation about which I know this. Yes, question.
So, can you just get rid of the S notation only because the two vectors are on the same language?
Well, so you're talking about how I got from here down to there? Yeah. Is that right? Well, it's so let's look at these one at a time. If I were to say, how do I say that with respect to the standard basis? Well, I'd have to represent T with respect to the standard basis, and I'd have to represent V1 with respect to this, et cetera, right? And so this is just what you get when you decide to rewrite this bottom statement with respect to the standard basis. And I mean, chronologically, I sort of did it backwards here, but it's the same point, yeah. Right. Okay, so what do I mean by saying that this is a convenient basis? Well, keep in mind, if I want to write a matrix representing a linear transformation, I need to know what is T of a basis. Right? I've got to pick some basis for the domain, and I'm going to need to know T of those input domain basis vectors. And, well, the thing is, I know T of V1 and V2. So this basis here, script V, is an extremely convenient choice of basis to use for my domain. in representing this linear transformation. All right, now what about for the target? What does the target basis do for me? Well, whatever comes out, I'm going to have to represent the output vectors with respect to some chosen target basis. So what would be a convenient basis to use to describe the vectors v2 and v1? Well, it's going to be hard to beat this basis, right? It's really easy to represent v2 with coordinates with respect to the basis v1, v2, right? That's going to be an easy one. Likewise, v1, easy to represent with respect to that basis. So now that's strategizing in advance. Let's actually put it all together now. Keep in mind the way we get this matrix here is the first column comes from taking the first one of these vectors, doing t to it, and asking for the coordinates with respect to that output basis, right? This is the formula for how to determine columns of a matrix representing a linear transformation. Okay, well, conveniently, this statement right here tells me t of v1. It's easy to write t of v1 using that statement. How do I write t of v1 as a linear combination of the vectors v1 and v2? Well, t of v1 is v2, so this is 0 v1 plus 1 v2. So 0, 1 becomes my first column. Okay, along those same lines, this statement here makes it easy to write down t of v2 with respect to the script v basis. Again, that's going to give me my second column. Whatever this ends up being, it's going to be my second column. Well, how do I write t of v2 as linear combination of v1 and v2? Okay, well, this thing here, v1, is clearly 1 v1 plus 0 v2. So 1, 0 goes there. Okay, is everybody on board so far? So still, we don't have an answer yet. We're not done. Does everybody see what I've done so far? Okay. Keep in mind our question. Our question was to find what is this matrix A. A represents t with respect to the standard basis. That's not what I just computed. I've just figured out how to represent t with respect to this other basis. So here we are in the situation where we understand t with respect to one basis. We want to find t with respect to a different basis. We need to do a change of basis. Right? And this is the formula that's going to do it for us. We're going to translate in the domain as needed, do the linear transformation the way we know how to do the linear transformation, and then translate in the target back to however is needed. Okay, so here's that formula. TSS, well, first translate from S to V. Do the linear transformation in V language. Out comes the result in V language. I don't want my result in V language. I want it in S language. Okay, so we'll translate from V to S. Okay. So some details then. Where are these matrices? Well, TVV. This is what I just computed very conveniently. That was the easy way to understand T. The change of basis matrices. Let's see here. Let me clean up my mess a little bit here. Change of basis matrices. Let's see here. I'm going to have to zoom out. So how do I compute change of basis matrix from V to S? Well, I need to represent the V vectors in terms of the S basis, which is already given. Right. I should say I chose my vectors V1 and V2 accordingly. Right. So it's easy to represent then that matrix is that. That makes it easy to understand this matrix because it's just the inverse. Right? The inverse of change of basis from V to S is change of basis from S to V. So those matrices are all easy to write down, and we have now just an arithmetic problem. With these being those, multiply these out, and there's your answer. Okay, now this is the first time you've seen an approach like this, and so you may be thinking to yourself, wow, that was a lot of trouble, right? I think I'll just go ahead and brute force this one in the future, right? But this is only a lot of trouble because this is your first time seeing it, right? What you'll eventually sort of get accustomed to is the idea that, look, sure, those are statements about, vectors in R2 and matrices, arrays of numbers. But look, let's just understand that those represent linear transformations. It's almost immediate, if only structurally, that those mean that. You just have to interpret accordingly. Right? Once you see that T of V1 is V2 and T of V2 is V1, again, it's right there in the structure of these equations. It's pretty much immediate then that in VV language, we understand the matrix that way. I mean, that's pretty quick. Again, once you're comfortable with these ideas. And once you have it at that point, now it's just a change of basis, which is just a couple of matrix multiplications interpreted accordingly. So this is actually a pretty reasonably quick way to do the problem. Okay, let this idea sink in your mind. I think this is really good practice. I'm going to show you another example of this kind of thing on the next page here. On the next page, we're going to make it a little bit, I'm going to say harder, and I don't really mean that, but it's going to look a little bit harder. Here, instead of V1 goes to V2 and V2 goes to V1, here none of these four vectors are the same. So what basis do you pick? I mean, the trick in this question was, hey, there's this really convenient pair of vectors, 1, 3, and 2, 5. 1, 3, and 2, 5 leap off the page at you here, right? Makes a clear choice of a basis to pick. Okay. So what do you do here? Well, notice there's no rule that says you have to use the same basis for both inputs and outputs. In terms of inputs, 1, 3, and 2, 5. Whatever basis I use for my domain basis, I'm going to need to know what the linear transformation does to those vectors. I know what the linear transformation does to 1, 3, and 2, 5. So let's let that be our domain basis. 1, 3, and 2, 5. I guess I'll have to zoom out. Will be the basis we will choose for our inputs. That's our domain basis. Now, the outputs, well, whatever basis I choose for my target, I'm going to have to represent the images of the transformation with respect to that target basis. What basis makes it easy to talk about 3, 2, and 4, 3? Well, how about the basis consisting of 3, 2, and 4, 3? Right, chosen for maximum convenience, maximum sort of effortlessness. Those outputs, 3, 2, and 4, 3, are really easy to write in terms of 3, 2, and 4, 3. Okay, so you make those choices. These two statements here translate like that. We have S of V1 is W1, S of V2 is W2. And those statements immediately give us that as our first column, and that is our second column. Right, the first column comes from looking at S of the first V vector. So it comes from S of V1. Specifically, I need to write S of V1 in terms of the W basis. How do I write W1 in terms of W1 and W2, well, 1, 0. Likewise for the second column. Does everybody see how this is just kind of a variation of the example on the previous page? Any questions? Okay. So it all ends in a pretty similar way. We already know that matrix very conveniently. Convenient by choice, right? By the way we set it up. We do have to find some change of basis matrices. So, all right, so the change of basis from W to S. Let's see, so from W to S, as a matter of just looking at what the W vectors were with respect to S. Change of basis from S to V. Now, well, here I'm going to have to invert a matrix. Change of basis from S to V, this is the inverse of the change of basis from V to S. That's the one that's going to be easier to write down. So I do have to do an inverse matrix. But anyway, that turns out to be pretty straightforward. And again, just a little arithmetic. Multiply some 2 by 2 matrices and we're done. Okay. All right. Yes, question.
You have your linear transformation goes from, let's just say R2 to R3.
Yeah. Okay.
Won't you end up with a non-square matrix? How would you take the inverse of that?
The change of basis won't be, though. So let's look back at our diagram. Now, that's a great question. So looking at this diagram, let's say that this is R2 and this is R3. Right, so the change of basis is going to still be from R3 to R3 there on this side. So yeah, so there's no squareness problem. Yeah, great question. Likewise in the domain. Okay. By the way, just a little bit of context. So remember, let's go back to the very start of the course. You remember. We did a bunch of linear algebra at the very start of the course, and that linear algebra led to more linear algebra, which led to yet more linear algebra, and this question of where is it all going and why do we care, right? And what we eventually found is that we were looking at some differential equations then in chapter 4, and well, to really understand those differential equations, we had to make use of the idea of dimension. And we had to make use of the idea of a basis and the idea of independence and span and trace it all back. And all that linear algebra ended up just being necessary to have the proper language with which to talk about how to solve those differential equations. Okay. All right, so here we are back doing more linear algebra. Where is this all going? And it's just round 2 of the same story. We're developing some linear algebra tools which are going to build and make more sophisticated linear algebra tools, and eventually all of these linear algebra tools that we're working on, it's hard to see it coming, but they're going to help us solve differential equations. Right? And differential equations are pretty easy to motivate. Again, the real world, anything in the real world where something's moving or changing is described by a differential equation, so it's very, very obviously, clearly, critically important to be able to solve differential equations, especially for engineers. Okay. All right, so believe it or not, this is going to help us solve differential equations. Okay, new topic, section 5.4. Weird little idea. It's hard to see it coming how useful this is going to be, but this is extremely useful. It's the idea of something called an eigenvector and its associated eigenvalues. So here's where it comes from. It all involves this equation, this seemingly, it's unclear why we would care about this equation. Why would it matter if we find an instance where a given matrix can multiply by a vector and you get a scalar multiple of the exact same vector? Now, curious, I suppose, right? I mean, certainly this doesn't always happen. It's, I guess you could say, an eyebrow raiser if it does happen, but I just want to make it perfectly clear, we do not yet have any particularly good reason to believe that it's actually worthwhile to be able to identify when this happens. We just don't have any context for that yet. So I'm going to ask y'all to take my word for it. The applications of this will come. It's going to take us a while to get there, but it ends up being really important to be able to understand when this happens, to be able to find vectors. These vectors here, with this vector, v, that has the feature that when you multiply by a matrix A, some particular matrix A, that what you get is a scalar multiple of that original vector. So these vectors, we call them eigenvectors. The corresponding value we call an eigenvalue. That's just lingo. Okay, a couple of little details. We do require that the vector not be the zero vector. If you think about it, it becomes kind of silly if the vector is the zero vector. Right? If the vector is the zero vector, then the equation becomes 0 equals 0, which is always obviously true. Right? Furthermore, 0 is equal to 0 no matter what value lambda you pick. It becomes this trivial, pointless, effectively meaningless concept. So the word eigenvector only applies to non-zero vectors. Okay. All right. Note also, for this to be possible, the input to the matrix and the output from the matrix, if they're going to be multiples of each other, as is indicated here, well, then they have to be of the same dimension, and that means that the matrix has to be square. Right? So when we're talking about eigenvectors and eigenvalues, we are implicitly only talking about square matrices. Okay. Really important. By the way, there is a related equation for linear transformations. If you can find an instance where this happens, then we can talk about eigenvectors of a linear transformation. We're not going to spend any direct time on that here, but it's morally same idea. Keep in mind we represent linear transformations very often with matrices, so you can see the connection there. Okay. Okay, let's talk about how to find eigenvectors and corresponding eigenvalues. So in some sense, we're going to want to solve that equation. Here we go. Solve that equation. Okay. It's an algebraic trick. It works very effectively. So here's the trick. First, notice that that's the exact same equation as this. Right? Lambda IV is the same as lambda V. Seems weird to want to group it together like that, but when you group it together like that, you can realize this second equation as specifically saying we are looking for the null space of a matrix. And we're already good at that, right? We already know how to find a null space. That's chapter 1 methods. Okay. All right. Problem. Null space of what? We still don't know lambda. All right. So there's, asterisk. That's, we're not sure where to go with that. But keeping in mind that this is not allowed to be the zero vector, right? We're not just looking for any old random null space. We're looking for a null space that we know is not empty. That means that this A minus lambda I matrix, since it has a non-trivial null space, that means it has to be a singular matrix. Which, if you flip back to there was that summary page at the end of chapter 2, and remember this is a long list that goes around to the second column, very long list of equivalent conditions. And having a non-trivial null space equivalently means that the matrix is singular, and equivalently that means that the determinant is 0. Okay. All right. And the reason we care about this is because that's a polynomial. This right here. You just multiply that out. We'll see an example in just a moment. But if you write down a matrix A and write down A minus lambda I, take the determinant, you're going to have a bunch of lambdas in there that get multiplied in various ways. You're going to have a polynomial in lambda. And so what we are doing here is we are looking for roots of a polynomial. And again, that's something we know how to do. Okay, a little bit of terminology, FYI. This polynomial is called the characteristic polynomial. That's just, again, a little bit more lingo. You might recognize that term, characteristic polynomial. We've used that term before. There was a special polynomial that we wrote down in studying differential equations. Basically, we had found a polynomial whose roots told us important things about the differential equations. So, characteristic polynomial. Here, we have found a polynomial whose roots tell us interesting things about something different. Here it's, eigenvalues for a matrix, not solutions to a differential equation. But anyway, it involves this is a polynomial that's critical to understanding a certain object, and so thus the term characteristic polynomial. There's another reason that we use the term characteristic polynomial that we're not ready to talk about yet. So just a little bit of foreshadowing. I think roughly, if I remember correctly, last day of class, I'm going to be able to make a different connection for this term, but we don't begin to have the tools for that yet. Okay, so example. Numerical example. Straight out of the book, by the way. Here's a matrix. That matrix A, right? Let me write down A minus lambda I. If you think about it, the identity has zeros in most places except for ones on the diagonal. So minus lambda I means just subtract lambda on the diagonal. Given a matrix A, it's really easy to write A minus lambda I. Just subtract lambda on the diagonal. Okay. Taking the determinant, multiply it out, collect terms, gives you this. We want to find the roots of that polynomial. It's easy to factor, and that gives us the roots, -1 and 4. So we're kind of halfway done. We found all of the eigenvalues. Right? These values, -1 and 4, are roots of the characteristic polynomial, and thus, being roots of the characteristic polynomial, they make A minus lambda I singular, which means A minus lambda I has a non-trivial null space, which means A will have eigenvectors for that eigenvalue. Yes?
Is A and lambda, are they like characteristic together, or does that work for any vector?
So the idea is we're starting with some matrix A. So A is the object that we're studying. Given a matrix A, it has certain values that are eigenvalues, and that's what we found here. So you might say that A gives rise to its eigenvalues. Yeah. Started with A, we concluded its eigenvalues. Yep.
Eigenvalues only defined for square matrices?
Yes, only square matrices. That's right. Yep, absolutely. Okay, so now we found the eigenvalues. How do we find the eigenvectors? Well, back up here to our little discussion, right? Once you've found a value of lambda that makes that determinant 0, that means that you've found a value lambda for which we can find non-trivial null space vectors of A minus lambda I, which will be eigenvectors of the original matrix A. Right, so the way we're going to find the eigenvectors, again going back up to here, the way we find the eigenvectors of A is we look for the null space of A minus lambda I. And let me emphasize, lots of students get confused on the inadvertently conflating two similar sounding things. We're not looking for the null space of A, right? Easy oops. If you just write down the null space of A, that doesn't mean that's not what we're looking for, right? We're looking for the null space of A minus lambda I. And likewise, once we have found these vectors V, these are not eigenvectors of A minus lambda I. They're null space vectors for A minus lambda I. They're eigenvectors for A. So make sure to see the connection between, but difference between these two equations as well. Okay, all right. So how do we find these null space? Well, null space calculations are easy. Y'all know how to do those. A minus lambda I. Let's see here. Well, let's take these one at a time. this eigenvalue of -1. Whoops. Stick that in here for lambda. So subtract -1 on the diagonal. Add 1 on the diagonal. And that gives you this matrix. We want to find the null space. Y'all can do that. Okay, and you end up getting all multiples of the vector 3, 2, as it turns out. Now, I know y'all know how to do this, but let me remind you, make sure that you're still good at that. Make sure that you can do that process, finding a null space. Now, that said, I'm going to show you another way how to do this, a really, really quick and convenient way of doing this that you haven't seen before, because it involves tools that we hadn't really talked about when we were doing this before. So it involves thinking about rank. So let's look at this equation. This is the equation we were solving on the previous page. Null space of A minus lambda I. Whatever vectors we get are our eigenvectors. Okay. Reasonable question. What's the rank of this matrix? And process of elimination, it has to be 1. Now let's just think that through. How do I know the rank of this matrix can't be 2? Well, because this is A minus lambda I. The whole point of A minus lambda I participating in this story is that we know A minus lambda I has to be singular. If it's singular, its rank can't be in 2 in this case. So it's not 2. Can't be 0. If the rank were 0, that means that the whole matrix is just zeros, all zeros. That's obviously not the case. So process of elimination. It's not 2. It's not 0. The rank is 1. Okay, why do we care about that? Well, rank nullity theorem, right? The dimension of the null space plus the rank has to add up to 2. Or said differently, the dimension of the null space is 2 minus the rank. Right, now this is a result from section 2.4, rank nullity theorem. So the rank is, I'm going to say, obvious by inspection. Therefore, the dimension of the null space that I'm looking for is obvious by inspection. Okay, now we found the dimension of the null space. We were looking for the actual null space. So this doesn't really cut it. Right? We want to know the actual null space vectors. But I claim that knowing the dimension is 1 is tremendously helpful. One-dimensional vector spaces have some really convenient features. For example, if you have a one-dimensional vector space, any non-zero vector is a basis. Right? Easy fact about one-dimensional vector spaces. So the fact that I can conclude the null space is one-dimensional boils this question of finding the null space down to just find any vector. Find any solution to the above equation. If I can find any solution to that equation, well, then it's a non-zero vector and a one-dimensional null space, and therefore it is clearly a basis, and therefore end of story. So instead of going through a process here to, hopefully, fingers crossed, maybe be able to, go through the, all the arithmetic without making a mistake, let me just see if I can dream up some vector that's in the null space here. Right? So not hard to persuade yourself. I think in terms of doing dot products with the rows. Right? What can I dot with 2, -3 to give me 0? And how about 3, 2? Right? That's the smart alecky observation of, hey, the 2 and the 3. If I put a 3 and a 2 and put a minus sign, hey, it cancels and makes 0. Right? We've all made that observation since Math 212. So it's easy to find a null space vector, a single null space vector, and therefore the entire null space is just all multiples of that. So anyway, this is a really neat trick. If you want to use this on an exam, I encourage it. All you have to do is document a little bit. Right, so what I'd want to see if you use this process on an exam is rank equals 1, dimension of null space equals 2 minus 1, therefore 1. And then you can say, therefore, boom. So let me me zoom out so you can see all this. Just document it that little bit. That's all you got to do. Okay, let's see a similar calculation here. What about that other eigenvalue? Oh, by the way, keep in mind what we're doing here. We're looking at this matrix, trying to find its eigenvectors. I already know the eigenvalues are -1 and 4. We just got through understanding the eigenvalue of -1. So what do I do with this other eigenvalue of 4? Well, again, subtract the eigenvalue off the diagonal. Look for the null space. This is that corresponding null space calculation. What's the rank of this matrix? Can't be 2. The matrix is singular. Can't be 0. It has non-zero entries. Therefore, the rank has to be 1. Therefore, the dimension of the null space is 2 minus 1, which is 1. Looking for a one-dimensional vector space. By inspection, this vector is in the null space. Therefore, all multiples of it makes the entire null space. Yep?
Were we observing that it's singular in a new way, or just that the determinant is 0?
Oh, yeah. I mean, if you want to just make the observation that the determinant's 0, that's also fine. I kind of like the process of elimination, but totally fine. Yeah.
So when you said it can't be 2 because you know it's singular,
yeah.
How did you know
Oh,
that it's singular?
no, I know it's singular because it's a minus lambda I. And lambda's an eigenvalue. Once you know lambda's an eigenvalue, sort of the point of that is that it makes a minus lambda I singular. Yep. Yep. Okay. 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 So, a little bit of lingo. Important lingo here. We were looking at this matrix, looking for eigenvectors. First we find the eigenvalues, then we found the eigenvectors, and we have them all written down. And let's just talk about how many eigenvectors did we find. And it turns out to be something important that we need to be able to discuss. How many eigenvectors did we find? And taken literally, how many eigenvectors did we find? Well, we found infinitely many eigenvectors. See, K can be any number. This is a whole one-dimensional vector space, so there are infinitely many eigenvectors. Well, okay, yeah, sure, but once you know that you have one eigenvector, I mean, obviously any multiple of an eigenvector is still going to work. So it seems kind of wasteful to say we found infinitely many eigenvectors because you're always going to find infinitely many eigenvectors, right? So that language has been kind of commandeered by the following. Admittedly, a little bit sloppy usage. What we say here, by virtue of the fact that the vector space of eigenvectors that we found, of course there were infinitely many of them, has a basis consisting of one eigenvector, we say we found one eigenvector. Taken literally, that's not true. Right? There's infinitely many, of course. But when people say we found one eigenvector, what they mean is the basis of what they found consists of one eigenvector. Okay, so we're going to say we found one eigenvector there, one eigenvector for the first eigenvalue, then we found one eigenvector for the second eigenvalue as well. So grand total, we found 2 eigenvectors. So heads up, I'm going to be using that language a lot. It's extremely standard. And just make sure to understand what it's saying, but also make sure to not interpret that literally. Right? Of course, there are always infinitely many eigenvectors. Okay. All right. So altogether, we started off with a 2x2 matrix. We got a degree 2 characteristic polynomial. Right? It was quadratic. So degree 2. There were 2 roots. Happen to be distinct. We know the roots are also eigenvalues. And grand total, in the sense of linear independence, we found 2 eigenvectors. And so you may notice this little pattern here, 2, 2, 2, 2. And you might even have made the connection already, thinking back to differential equations. Let me remind you of how wonderful the pattern was in differential equations. we were looking at, let's say, an nth order differential equation. The characteristic polynomial was degree also n. The total number of roots was also n, once you include multiplicities. And how many solutions did we find? Well, we had to do some work to find some of those solutions, but subject to linear independence, we found n solutions. So nth order, nth degree, n roots, n solutions. It looks like the same thing is happening here. And I am very sorry to have to report that this is not always the pattern that holds. So it's just sad fact. This just doesn't always work. This is not like solving differential equations in this way. So here's the easy counterexample. Let's think about that innocent little matrix right there. Fairly harmless looking matrix. Let's play the game. There's the characteristic polynomial. Easy algebra. It has one root. Okay, now I hear you. It has one root but with a multiplicity. So it's kind of like there's two roots. Right? Sure. I kind of feel like this one root, this one eigenvalue, I kind of feel like it owes me two eigenvectors. After all, it's really kind of two roots in the sense that it corresponds to two factors. Well, I'm not going to get them. Write down your null space equation. Go through, play the game. You get one eigenvector. And I emphasize, it's not that I've only found one and there are other eigenvectors that we'll find by other means. Nope. Nope. This is it. That's the only eigenvector. So that pattern, again, sadly, just doesn't hold. So be aware of that. Now, sometimes it does. Sometimes you get lucky. So here's a matrix, and I'm going to skip the details because it's the same pattern over and over again, but you can write down the characteristic polynomial. Turns out to be this. Not too hard to check. Here's your roots. That first root has multiplicity 1, and you get, correspondingly, and I keep not going down far enough, you get correspondingly one eigenvector. So multiplicity 1, you get 1, as hoped, expected, whatever you want to say. On the other hand, let's look at this other root. Here, let's look at -1 as a root. Note the multiplicity is now 2 for that eigenvalue. And go through this process, and you get 2, in the linear independent sense, you get 2 eigenvectors. Multiplicity was 2, you get 2 eigenvectors. Again, just as you would sort of hope. So sometimes stuff works out the way you'd hope. Sadly, it just doesn't always. So a little bit of terminology. This is just kind of summary of stuff that we've talked about. Eigenvalues are roots of the characteristic polynomials. Eigenvectors are in the null space of A minus lambda I. That's just calculations. So a little bit of lingo. That null space, instead of saying every time the null space of A minus lambda I, it's easier. Just give it a more convenient name. The whole point to this vector space is that it's a vector space of eigenvectors. So we call it an eigenspace. Just terminology. Eigenspace means the null space of A minus lambda I corresponding to that eigenvalue lambda. Okay. All right. Let's see here. Oh, gosh. You know what? I don't have time to get started on anything else. I only have 30 seconds left. Very often I go a little over. Let's go a little under today. Good stopping point. See y'all on Wednesday.